Thank you again. Uh, Let me know if I need to increase the font size or this font size is uh, clear enough. And since one of you have mentioned that you can also zoom in on your side too, so I will assume that this is okay. If it is not, please let me know. Okay, so we will start today's lecture. So today's lecture we will be seeing the last one ridge regression. Let me just quickly go over it once. I think that would be nice if we go over it. I think this is not. Okay, let me see. This is the one. Okay, so we yesterday last class we looked into regression, regularization of two kinds. This lasso ridge regression where we weight all these beta knots, that is wi's whole square. We weight these with lambda times wi square, and then lasso or L1 regression, that is lambda times mod of wi. All these weights that you see, we call these as weights. These all these wj's are weights of these model, and we call it weights. And now we'll see two kinds of regularization in today's tutorial, which is ridge and lasso. And we also remember that model complexity is nice to have. So when you are not when your model is not being properly explained through linear models, we want your model to be complex. But if it becomes too complex, it starts overfitting the data, and you see a high variance in your uh, model. High variance also means that it has multiple curvatures in the system, in the modeling itself. You will see that the model has become sufficiently complex. And we saw that regularization can be used to control the model complexity. When your regularization is zero, when that lambda is this term, sorry for so many slides, please. So lambda is this term. If lambda is close to zero, that means there is no regularization term. You have your entire model. That simply means that model is full complex. It's like the model complexity is very high. And when lambda is equal very large, you don't have any model complexity. The model becomes very simple and it's close to linear. So you want something in between to make sure that model is good representative of the data set and it's not very complex. And we also saw that when lambda is very high complex, your training error is close to zero, but your test error is sufficiently high. Even when your model is not complex, your train and test error both are sufficiently high. In this case, this numbers does not is not the correct. We assume so your train and test error are sufficiently high. We'll see these points in play when your lambda is when your model lambda is zero, your model is fully complex. How will your data set look like? And when your lambda is very large, your model becomes superbly simple, and the train and test error both are will be sufficiently high. What we want is something in between that actually justifies your data set properly. So this is one we will see. The other part we will be focusing on, I think if time permits, we will see cross validation, or else not. We will see cross validation in another tutorial. So today's entire focus is on just to understand how ridge and lasso regression, these two terms, play a role. Okay, now let's look into these terms. And the other part, the other part that we will be looking into is this difference that we have created a table here. We will go through this table again while doing the lecture, while doing the tutorial. Okay, so let's start today's tutorial. So we have this, initially we will actually just import all the libraries that we have. Now this is how our data set will be looking like. So we will we will just fix one of this random seed so that we always generate the same data points. Now we have X, we have Y, we have added some random noise U. Remember that we have always have some function and some random noise will be there, but you cannot always measure the function exactly. So you have some random noise in the system. And if you plot your equation, this is how the data set will look like. For X, this is the Y that you have generated. We have generated 1000 data points now. So this is how the plot looks like. Your best model should be something in between, some line that goes through all in the between these data points. So something like this would be the best model that describes this data point. And the best model equation would be 2 plus 25x to the power 5 is the model equation. That is the best model that describes these data points. And these are noise that you cannot model in general. And in real system, we see such noise to be there. You can think of it that when you actually use your cell phone and you talk to your friend, the signals that are sent through your cell phone and it receives to your other's friend on the other side, there are some noise that you cannot model. Those noise can come through the signals goes through so many different places, different temperature. uh, Air also adds its own noise. There are dust in the environment, other noisy sounds like honking sound or horn sound from the traffic. All these add to the signal noise, and when your friend receives your signal, they receive the actual message, the true data point, and some noise in this signal. So these noise are generally unavoidable. You have to live with the noise. What your goal should be that can I model the correct equation? Can I get this correct equation properly? You don't necessarily want to model this noise because these are noises that are added to the system. You don't want to model these. What you are interested in, can we model the true nature of the signal? And your model's focus should be to figure out what is the best line or best model that explains these data set. Okay, so without any further ado, so this is what your data points are. So this time there were thousands of data points. Now we only draw 25 data points here. So x is 25 data points and y is just the same equation, 2 plus 25 times x to the power 5, and we added some random noise, and this is how the data looks like. So you see, you have your data points, but okay, so here we have added a significantly larger noise here, which is five times the noise we have added. So you can control the noise too. If you just change this noise value to 1, it will add less noise there. If you add more noise, say if you want to make it like super noisy, so if you add 100 or so, so you will see that it has become simply random. There is no signal that is there now anymore. So if your noise is sufficiently very high, it simply means that your main signal is very difficult to recover from. Your main nature of the data is sufficiently very difficult to recover from. So let's, for the sake of our experiments, we assume that there is a moderate amount of noise, which is 5, and we can still see that we can still be able to recover the data though, model though. So it should be something passing through in between these points. Okay, so this is how our data point looks like. Now, what we will do is that we will first split the data point into training set and a test set. So we will use the inbuilt function, that is train test split function. It is inbuilt function of the library. So we chose a test size of 20%. Okay. So 20% is the test size that we chose. So out of 25 data points, we will 20% will be chosen as the test data set, and the remaining 80% would be train set. Okay. So now we will just create this train test split. So we will now sort them, and we will see how this train test split looks like. So we have this train test training set x and y, test set x and its corresponding y, and we will plot these data points now. So this is how your train and test data looks like. Train data is something like this, and test data are slightly, these are the 5 data points, 1, 2, 3, 4, 5. 5 data points here, and this is your train data point. So you will be training on these data points, and you will be testing your accuracy, testing your prediction error on these 5 data points. Now, this example is also perfectly good for cross validation because 5 test points may not give you the actual error of the model. So you can actually do cross validation here in this example. But for today's lecture, to understand this lecture properly, we'll just not use cross validation for time being. We'll just focus on these 5 test data points. These test data points will not be changing as in cross validation iteration 1, 2, 3, 4, 5. We will only be focusing on iteration 1. No, there will be no multiple iterations here. Okay, so you have these training data and you have this test data now. Okay, now let's look into this. Okay, last time when we actually did our linear regression, we created our entire equations. But now since you have already learned how to do linear regression, we will directly be using the functions that are available in the scikit-learn library. So what does polynomial feature 1 means? It simply means this. So say your x is of size 1. So x is there is one dimensional scalar. So simply the model y model is equal to w naught plus 1 second. So your y naught model is w naught plus w1 times x. So w1 and w naught are the parameters of the model. This is w naught and w1 are the things that you want to learn. So polynomial feature 1 simply means this. Okay, so there is degree 1, x to the power 1. So if I write polynomial feature degree 2, it simply means w2 times x square. Okay, so your model will become more complex. So remember our lecture on this complexity. So we have theta naught. So this is polynomial degree 4. Okay. So if you want to create this equation, you just if you write polynomial feature 4, it will create that 4-degree feature. Okay. So we were using polynomial degree 1. Polynomial degree 1 is this linear line w naught plus w1 x. This is the linear line equation that you want to find. So we want to find w naught and w1. So we created this polynomial feature. We will apply linear regression, and now we will fit the model with training data x train and y train. And now we will use the x train data to predict the x train sample points. Similarly, now these are for plotting. We will now plot these x train and y train data points now and see how it looks like. So now it's a simple model of degree 1 polynomial. We will create similarly a 10-degree polynomial. So remember this is degree 1 and this is degree 4, but now we are going to create a 10-degree polynomial. 10-degree polynomial will fit a linear regression, will fit the model. We will call this 10-degree model as a complex model and a 1-degree model a simple model. Now we have x train complex. Now we will fit the complex model. We'll find w naught and w1. When you call fit function, it will calculate all the w naughts till w10. We'll predict x train for this complex model, and now we will plot these data points, the complex data points. We'll call complex model with degree 10. Okay, so this is how it looks like. When you try to fit a linear line, it actually just simply fits a linear line. But when you create a degree 10 polynomial, look how it is trying to fit. It's just trying to try to fit all the data points as it can, right? Now I will wait for the here for a while to see if there are any doubts, anything that you are not able to follow, or you want me to do some more experiment in this domain to show. Any question? Anything that was not clear till this point? Okay. So I will assume that this part is clear. So we will do one more experiment in this. So here we have created a 10-degree polynomial, right? Let's create like say 50-degree polynomial. So now the equations will look like this. Your model complexity y model is equals to w naught plus w1 times x plus w2 times x square, and it goes till w50 w50 times x to the power 50. Okay. You see, it goes to x to the power 50 now. So all w0, w1, w2 till w50 are the one that you want to calculate. You want to know these values such that it best explains these data points. Let's create 50-degree polynomial. So now it became a 50-degree. Okay, so let's write degree here. Degree is equal to 50. And let's set everything here. Degree. Okay, so now let's create a 50-degree polynomial. Look what it did. It became even more complex. You see, a simple model and a 50-degree polynomial is trying to fit all the data points as it can. Now you see that the model actually, the data points had some noise in it. Now your model, as you have increased the degree of made your model super complex, it has started to fit the noise also. It is not just fitting to the data point, it is also starting to fit to the noise too, because the data has your signal component, your true component, and some noise. Now it has started to fit to the noise too. So let's decrease some degree here. So let's make the degree to say 20 and see how it is look like. The model is still sufficiently complex, but better than uh, what is 50, right? It's still better than 50. It's still able to explain data, but this is still very poor. What we are currently doing is manually checking which model fits which model explains the best. So this is, it looks better though, but still sufficiently complex. This is still sufficiently complex. Let's make it a degree 5, which is the one that we, now you see it is much better, right? It better explains the data. It's still able to explain through the data points. Now, if you make it degree 4, how it looks like. Let's see. This is also better. So now you see that if you make your model sufficiently very complex, it start fitting to all the data points, or specifically it starts fitting to the noise of the system. You see, if your degree was so high, like say make it 50, you see there are so many multiple curvatures in the system now. It's trying to fit to all the data point as it can, right? Okay. So let's can we just move with 50? Let me see if there is no such problem. There should not be any such problem there. Okay, let's make it with 50 then. Let's go with. Okay, let's make it. I think we should be able to go with 50. Okay, so let's try this now. Yeah, let's try this now. So now we are going with degree 50, like make it super complex, a very complex model, and a degree 1 super simple model. So now we are at these two end, a very complex model and a very complex model and a very simple model, a degree 1 model and a degree 50 model. Okay, let's go ahead with this. So it is now fitting to all the data points. Let's check. Now remember what we said before. When you have a very complex model, which is lambda equal to 0, the training error is close to 0 because it's fitting to all the data points, but your test error is sufficiently large because it has now got into it has so many curvatures that it is not best explaining the data set that is had not seen before. And similarly, when your model is very simple, it simply is not explaining the data itself. Your data has a curvature, but it is a straight line which does not explain the data. So both your train and test error both are high. Here, train error is low, but test error is high simply because it cannot explain the data points that it has never seen. Okay, let's calculate your train error first. So we are calculating mean squared error. Uh, if you remember what mean squared error, I don't know whether you remember what we did this thing in the last lecture. So what it does is that, okay, let me just write this, what mean squared error is. We did this mean squared error tutorial in last tutorial session, but let me just do it again. So this is your y minus y predicted whole square. And you calculate, you sum this thing entirely. No, you just calculate the average of this. Average of all the data points which goes from all the data points. So you have say 25 data points here. So for all 25 data points, you calculate y minus y predicted, true y minus the predicted y whole square. This is the error square and average that. So this is the average mean squared error. So mean squared error. So this calculates the average mean squared error. And if you calculate the average mean squared error, look at this. A simple model has 33.10 error, but a complex model has training error close to 0, 10 power minus 6. So whenever you see E, assume it is 10. So 1.02 into 10 to the power minus 6. So the complex model has close to 0 training error and simple model has a high training error. Can you see? As predicted, a complex model has a very low training error and a simple model has a high training error. చెప్పేసి ఆ ఊళ్ళో ఇంతమంది చనిపోతున్నారంటే దాని కారణం తెలుసుకోవడానికి వెళ్ళాం కానీ అక్కడ మేము Hello? Okay. So this is what we see. Okay, now let's look into the test predictions. So now we will use a simple model, a degree 1 per model, and this is degree 50 though. Okay. So we'll use a degree 1 model, a simple model, and test the X test value. We'll add those X test and see what Y test prediction is there. So Y test predict simple, so degree 1 model, and now we have a complex model. We will take the complex model, we'll use the X test to predict the Y test of the complex model, and we will plot these models. And we will also calculate, okay, let's not do calculation here. We'll do this calculation in the next line. Okay, let's just remove this calculation here. Okay, so we have these models. So we have this model. So we will use this and plot. So the green dots are the test data points, and you see a straight line is trying to fit these data points, which is still okay, it seems like. But look at these test data points. So one is at 0 and another one is at 3, but these are able to fit these data points. Degree 50 is somehow able to fit these points, but it is not able to fit this. And we will see the error between them. So you see, the test data has an error of 60, but your complex model has a mean squared error of, look at the number though, it's in 10 power 6. The reason is that the scale is not 0, 1, 2, 3, 4. It's actually 10 power 6 though. So look, it's this point and what it has predicted, the gap is in the 10 power 6. It's actually minus 3.10 minus 3 into 10 to the power 6, and that's what you are seeing here. Look at the test error in a complex model. So your model is not able to predict, the complex model is simply not able to predict on unseen data points. A simple model, even though This is also failing because it is also giving you a very high test error. So I will wait here now to just to make sure that everyone is able to follow. This also proves that you need test and data point. Training error on a complex model was extremely low, like 10 to the power minus 6. Remember, the complex model training error is so low, and simple model also had a very high training error. Complex model ended up fitting to the noise of the system. Now here, the complex model, if you test your complex model on unseen data points, which was not used to train the data set, it starts giving you extraordinary high errors simply because it does not know how to explain the test data points. If your model was correct, the test data or the unseen data points should also have the low error if only your model was able to best explain your model. Look at the simple data point. The simple data point has a very high test error too, which is close to 60. So I will wait here for a while to see if everyone is able to follow this path. Is there anything am I explaining it too fast, too slow? Uh, uh, is this thing clear? Because please, if someone can confirm, say something, or am I not? If you want me to explain again, I can explain again. If this is okay, not okay. Okay, let's do one more experiment. So here we have done a very complex model which is trying to explain the data points. We saw that degree 5 or degree 4 was best explaining the data set, right? So we have this degree 5 model which looks a good model. You say degree 5 is good or degree 4 is good? I will need help now. What do you say? Will you call degree 4 a good model or degree 5 a good model for you? Can someone respond or say something? Degree 5 looks like this. What we are trying to do is that let's choose less complex model and see what is the error on test data set. We will do the same process again and see how it behaves now. So let's for the time being assume that the degree 5 best explains the data set, which looks okay to me at least. It does not look super bad. It looks okay. Let's calculate the simple train error. So you see the train error on the complex model is lower now, 14 though, than the simple model. But it is definitely the super complex model had close to zero error. It has now 14 error. Okay, let's live with this error though for the time being. How does it do on the test plot? So this is how it looks like, okay, which has minus 10 here and it is 10 here. It seems like it will have more error. Let's see how does here. So now the complex model has still have 132 error. Simple model does much better than your complex model. So you can see that the complex model is still has a very high error. It fails on your test data set. Okay, now what we will be doing is how, so you can see that manually selecting which model works best is sufficiently tough. So if I make the model complexity 3, and this is how your data point looks like. Let's try fitting all the data points again. So you see the training error is 16, which is nice, but let's see how does it behave on the test data point. And the test data point is, oh, okay, now it is better. It's 23 now. So you see, it's sufficiently difficult to manually select what complexity of the model we should check. Whether we should keep 50, whether we should keep 3, whether we should keep 4, whether we should keep 10. Manually controlling this value is sufficiently tiring. And in this case, we have only one value x. What if we have multiple x's? Your data point is not just made of one x, but multiple features. Say, for example, to predict y, you needed to know the age of the person, the height of the person, the weight of the person, to predict whether the person is healthy or not, or to give that what is the BMI of that person. You need weight and height, definitely, right? And say, for example, for some reason you also require age, so you have three features now, not just one but three features. And to make make a polynomial degree of with three features will become even more complex. So to control to actually do it manually, it's sufficiently tiring. So we need a proper way, a proper mechanism, which we will look into the regularization part, to understand how can we control the model error. Okay, so now we have seen a complex model. A complex model will have a very low train error, but a very high test error. Similarly, a very simple model will have both train and test error to be sufficiently high, as we saw here too. So 60 is the one. A simple model has a 60 test error and train error of 33 or 34. Test error of a complex model is sufficiently very large, and the complex model's train error was close to zero. So I will stop here again. Uh, if this is okay, then now we will see uh, the trade-off thing. Okay, so let's look into this. Oh, I think I will end. Okay, so bias of a system. So bias is defined as the inability of your ML model to capture the true relationship. If your model is very simple, and you see a very high error on your test data set and trained data set, it's simply because your model is not able to capture the true relationship between the data set. But when you see a variance error, is that your model, difference in fit between the different data set of the same distribution. What it simply means is that your model is completely fitting your training data set, but when it comes to a unseen data points, which the model has never seen during the training, it's completely not able to predict because it has become extraordinarily complex. You see a very high variance in your answer. So that's what it means, bias and variance. Bias error you see when your model is very simple, variance type error you see when your model has become extraordinarily complex. So here we have seen 50. Okay, so let's look into the complexity now. So this is how your 50-degree model looks like. A simple model is a straight line. A 50-degree polynomial looks like this, tries to fit all the data points on the training data set. Okay, so underfitting and overfitting. What is this thing? Okay, so a simple model has a high bias, and simple model has low variability. As you can see that there is not much curvature here, so there is no variability in your prediction. It's very simple straight line model. Underfitting, it's underfitting the system. Overfitting, a complex model has low bias, meaning that it has all the points are predicted accurately. On the training data point, it's predicting everything exactly. So the training error is close to zero. But the model has very high variability, meaning it has multiple curvatures, and on test data set, it will show extremely very high error. Ideal model is the one which has low bias, meaning it is able to give lower training error and also low variance. That is, on the test data set, also low error. So that's what you want. The ideal model should have both training and test error low. Okay. So this is the one that we want to understand. This is the one that we want to get to. Ideal model. Okay. So here what we will be doing is, so here what we will do is that we will go with all the polynomial features. So we will create a polynomial degree of 1 to 10. So it will go from degree 1 till degree 10. So we'll go from simple model till complex model of degree 10. And we will fit our training data set. We will fit, once we have fit our training data set, we will actually use our training data set, calculate the x training data point and y training x test data points. Once we this fit and transform is just simply transforms your x to into a proper form. There is nothing much it does. We'll use this linear regression model. We'll use this polynomial feature and fit your polynomial feature in the training data set. We'll pass it to the training data set. So this is polynomial train data set into a linear regression of degree 1 is going through. We'll predict the training of the degree 1, currently is first iteration. We'll predict the test of the model. We'll calculate the mean squared error. Now we have added a square root over it, which calculates the root mean squared error. So let's not complicate it. Let's just focus on square root error. But I think the numbers will become sufficiently large. Maybe that's why the plot may not look correct. Okay, let's just remove this part. We don't need it for the time being, let's just say. So let's calculate the mean squared error. Okay, so this is how it looks like. So when you have your training error, as your model was becoming complex, your error was reducing. You see, your train error, the blue color line, as your degree 1, you saw 33 error. Degree 2, it became around maybe 14 or something. Degree 3, it is also at the same time, same place, but slightly lower. But as you increase degree 4, 5, 6, 7, your training error it keeps on going down, but your test error has shot up. It has become significantly very high. Okay, let's actually plot these numbers properly. So let's not limit this part and see. Let's you see what is happening now. For degree 4, 5, it is there, but as your model complexity kept increasing, your test error ended up increasing significantly very high. You see, your test and train error gap. So on a test data set, the model is simply not able to predict, and the error is very high. Okay, so now let's look into the mean. So now you have seen the mean squared error part. Let's now just see the this is root mean square. It will also explain the same variability, but it has a nice figure though. Here you see the error is decreasing on the training data set, but on the test data set, after 2, 3 is better, and 4 error increases. You see, so you can say that the degree 3 or degree 2, whichever you choose, either maybe 3. So 3 has lower training data set, a lower training error, and the test error, and anything above have very high training, lower training error but high test error. When the model is simple, you have both high test and train error, but when you have uh, very high complex model, you have a very high training test error but a low training error. And this was also the same thing that you saw in your example 2. Where is this thing? Yeah, there you go. You saw a very high, when your model is low complex, you have a very high bias error, this green color line. When your something in between is the one that you want to prefer, and when your model became very complex, you again have a very high error. So both these error, when your model is very simple or when your model is very complex, both have very high test error. Something in between is the one that you want to find out, and this is one way to find out when you move where to stop. So this is all your manually you found out that 3.3 is the one that gives you the best model. I will stop here a bit to see if you have any doubt. Okay, so let's move forward. So now we will see regularization. So you have your ridge regression. So this is your y minus the equation w naught here. Okay, it is w naught plus some all the equations that you have. So whole square plus lambda times all the weights square. Here this is ridge, and the way mod of that is the lasso. Now let's use ridge regression and lasso. We will again do the degree 50 thing. We will not, let's make it degree. Okay, let's just, for the timing, let's just set degree 10, degree here, and degree here, degree here. Okay, I think this is better now. Hmm. So now we will have a degree 10. As you saw, that the training error is very low, but the test error is extremely very high. See, you have the training error is low, but the test error is very high. And degree 10 itself, you don't have to go till degree 50. So let's look into, keep the degree 10, but we will now do something simple. We will not use different types of model, but we will try to control the model complexity by adding regularization. Rigid regularization, which is lambda times weight square, and lasso lambda times mod of weights. So we will create this ridge model by adding ridge, and alpha is the is lambda. Okay, let's just add lambda is here is alpha. So in the ridge equation, they call lambda as alpha. It's the default name there. So we have set lambda equal to zero point 0.1. I think for simple clarity, let's just write lambda. LAMBDA 0.1. Okay, so let's use lambda here. Let's just make sure that no one gets confused. Okay, so you see, when you actually put lambda 0.1, you're able to control the model complexity now. Initially, initially on the test data set without lambda, let's just put lambda equal to 0 to make sure that you see, without lambda, you have a very high uh, loss. Ridge loss is also very high. Trading loss is also sufficiently high on the test data point. But when you add some amount of lambda, when you make lambda very large, let's just make very large lambda, you'll see that the model has become even more lesser complex. You can even control even more if you by doing adding significant large lambdas. Okay, so the lambda controls the complexity of the model now. You can see by changing this lambda value, you can actually control the complexity of the model. How complex and how less complex you want your model to be. Now let's calculate the ridge training loss. So your training loss is close to 17, and your test loss of the ridge is close to 30, which is much better, because look at the training loss of the lambda when the degree was 10, your test error was above 40 or so, but not above just 40. It is actually a mean squared error though. Let's just make it mean squared error. Your test error was so high that you can't even see here. Yeah, see, when your degree was 10, it is close to 8,000 or so plus. So now when with degree 10 with lambda equal to 0.1, you're able to make your test data set error 30. You see, your lambda is able to control your model complexity, and not just it is 30. On the training data set too, your error is 17, which is lower than what it was before. So lambda is able to control your model's complexity and make sure that you are able to find a good model representation. Now let's look how the plot looks like with degree 50. And okay, so this is degree 50 though. And what is the degree here? Degree 10. Okay. So this is degree 10. Now you see. So when you have a degree 10 polynomial, why is it called degree 9 though? Um, Wait a sec. Sorry. Okay. So this is how it looks like. So when you have your model, now you will actually try to see the complex model with degree 10 and your ridge model, how does it looks like in the plot. So this is your degree 10 polynomial, which is trying to fit to all the data points, but your degree 10 polynomial is now trying to regularize and is trying to fit the model best. You see, this is the nice looking curve that you created your data set from. Let's recall that our data set was this nice looking curve. That's what you always wanted, and no one was able to figure out. But when you added your regularization term, it's able to figure out your nice looking curve here properly. You see? Okay. So even when I make it a degree 50 complex model, uh, we draw this model 50. This is your regularization. Now let's plot. What is this plot for? This is a complex model, rich predict. Oh, so this is the same model though. On the test data set now. So this is on the test data set. So here you see that the error is significantly 10 to the power 6 kind of error. Here the error is now slightly lower. Okay. So now we are towards the end now. I will ask anyone if you have any doubt. So let's just go back to degree being degree 10 because I have changed so many plots everywhere. Okay, so we have our entire model now. So this is a complex degree 10 model, and this is how when you fit degree 10 with regularization, this is how nice looking curves you will get. And similarly on the test data set, this is how your test data set fit will look like. Now, I will wait to see if you have any doubt here. So Ridge and Lasso, either of them will be able to control your model's complexity. So that's why we need regularization. That's why we apply regularization. If there is any doubt here, anything that is not clear.
Sir, if we want to know the suitability of ridge or the lasso, is there any parameter on which we can decide?
Acha, which one to choose? Lasso, you should choose
Yes.
a rigid. Okay, we'll come to this part now. So till this point, I think you all are able to follow, right?
Yes, sir.
Okay, so now let's look into the last column. So we will now look into this. We will now be almost be coming to this section now. What it does now. Okay, so what we are trying to do is this model. Okay, let's first explain what is this point. So here we are creating a synthetic data points. We are just creating 1000 samples features. 1 second, please. Just a 1 second. Okay, so now what we are trying to do is that we will create 1000 sample points and we will create 10 features of which only 5 are informative features. The 5 features are actually the true features that we will need to predict our points, and other 5 are just useless features. Say for example, if I have to predict your knowledge in say this data science, do you think does it matter what is your name? It does not matter, right? Whether your name is Ritu, whether your name is Piali, whether your name is uh, Srishti, it doesn't matter what your name is,
Um, Maybe
right?
because it's not unique. Is that the reason?
And no, it's not unique. Is not the reason. It's like it's uninformative. Whether your knowledge
Okay.
in this course is not correlated with is does not have no relationship with your name, right?
Okay. Hmm.
So what we are creating is that we are having 10 features, of which five are useless information. Five are as useless as there is no need of that. If you remove those five features, it's not going to affect your prediction. Only five features are needed, or only five of them are actually informative. So five of them are uninformative, and we will add a noise of zero point 0.1. There you remember that a noise was 5 or something. So here we are just adding. You can control the noise, and this is just simply fixing the random states now. So we will take some 1000. We will create a 1000 data points with only 10 features, and only five of them are informative. Five of them are useless. We want what our goal is that we want to make sure that our model is somehow able to uh, find only these five informative features, and remaining five features they should be able to ignore these five features as soon as possible. That makes sense, right? You don't want to focus on these uninformative features. We only want to focus on these five informative features. You don't want to focus on some random useless informations like your name, at least in predicting whether you understand this course or not, right? Okay, so this is how we have created the data set. Only five of them are informative, five of them are useless. We first create training data set, X train and Y train, X test and Y test. We have train and test data set. 20% of them are train set. Now we are having alphas here now. Alphas are your lambdas. Remember the lambdas are the one that you want. So now we will have minus 6 to 6 with 200 spacing. What it means is that it will start from in a log scale though. So it is 10 to the power minus 6. It starts from 10 to the power minus 6 to 10 to the power 6. So it goes from 10 to the power minus 6 to 10 to the power 6. The reason it goes from there is because of the log space. So it has created in the 10 to the power minus 6 till 10 to the power 6. And in that space, you will only take 200 points, equally spaced. So it has 10 to the power minus 6, 10 to the power minus 5, 10 to the power minus 4, till 10 to the power 6. This is how it will go. So you have your alphas here. You will start fitting each alpha, one alpha in the ridge and one alpha in the lasso. Now we were the question that one of the student has asked, that when to choose what. This is exactly what we are trying to understand here. So ridge and lasso, we use the same alphas, and we created our model. We are fitting our model on the X train and Y train. Now we are predicting our coefficients. Remember, the coefficients are simply this values. Okay, so the Y model, this is what it is. Y model is equals to W naught plus W1 times X plus W2 times uh, X2. This is X1. We are creating a linear model though. This has polynomial degree 1. W3 times X3. I will ask question though. Just a sec. Just let me just write this. X10. Can anyone tell me what is X1 till X10? Look at this thing. Can someone tell me what is X1 till X10? What are these things? Where did we all our previous example only had W naught plus W1 X. This was degree 1. What is X1, X2, X3, X4 till X10? What are these X's? Okay. So these, remember that when we said that we have actually 10 features now. So each person, each data point has 10 features, and each of these features are x1 feature 1, x2 feature 2, x3 feature 3, and x10 feature 10. That's what your number of features were, right? And among these, only 5 were informative. So if I say that, let's just write few more points. X4.
Are they same as the theta we were taking in the equation?
Yeah. These are same. All these are different naming thing. So they are
Oh,
all
no,
exactly.
no, okay. So these are the thetas, right?
Yeah, these are the thetas.
Okay.
So x's are not thetas. X's are just features. So
Okay, sir.
x's are these x. Where did it go? X's are this x, small x. This is your feature. Thetas
Okay.
are your parameters that you want to learn.
The okay.
Okay. So this x10 is simply these values: x1, x2, x3, x4, x5, x6 till x10. So these are your features that the data already has. Like you are, for predicting whether you understand this course, what we need is how much time did you spend on this course. This is one feature. How much time, how much self study did you do? How much did you attend all the classes or not? How much self study did you do? Whether you did all your assignments properly or not, whether you understood the lecture properly or not. Say these are there are 4 features now to make sure that what is the grade that you will get on this course, to predict what is the grade that you will get in this course, right? So there were 4 features to predict one value. So here similarly we have 10 features: x1, x2, x3, x4, x5 till x10 to predict one value, y predict, y model. Okay. And we said that only 5 of them are useful and 5 of them are useless features. You will never need those 5 features. Say for example, to predict your grade, I don't need to know your name, your roll number. I don't need to know your roll number. What I need is this, only these 4 features: how much time you spent in reading the course, how much self study did you do, whether you did your assignment properly or not, whether you understood the class properly or not. Only these 4 information is sufficient for me to predict your grade in the course. I don't need your name, your roll number. I don't need these information. So these 2 informations are useless features. So in this data set, we have five such useless features. Only 5 of such features are important. Okay. So now this, what am I storing here? Rig coefficient just stores W naught till W10, not excluding W naught. It is not storing W naught. It's only storing W1 till W10. W naught is not stored in this value. So only W1 till W10 is actually being stored here. So ridge, when you call this function, it will store W1 till W10. So now you are storing all these functions in this ridge coefficients, and you are changing alphas now, where the very different alphas, to see what is happening there, and you convert that into an array, and now we will plot these things, how it looks like. So you see, when your regularization is close to 0, that your model is extremely simple, then you see that even when your regularization was 10 to the power minus 6, you're still only seeing 1, 2. This is rich though: 1, 2, 3, 4, and 5. Only 5 features have value greater than 0, and all the others are close to 0. There are some activity there, but they're close to 0, right? But in lasso, and it is taking time to actually go towards 0, which one is the important, and it takes till 10 to the power 3, continues to drop. But only 5 features are rich is sufficiently able to find which are those 5 features that are important, and every other features were useless, so they directly put them to 0. Okay. But look at lasso, how lasso is behaving. Lasso, it is also able to identify when it was 10 to the power minus 6, when the lambda was 10 to the power minus 6. It is also able to identify those 5 important features, on all the other features were set to 0. But look at what it is doing. Whichever features, whichever parameters w1 w2, whichever parameters that were of less important, they directly put them into zero. They don't take so much time to go 10 to the power 5, 10, 6. They're not taking so much time to make it to zero. They directly made it zero. All those less important features. They said that all these features are important, but it is not contributing much. We will just remove it. 30 was contributing the second best, so it became zero later on. And this blue was the most contributing. It contributed almost initially 55 or close to 60. It went to zero late, simply because it was contributing the most. So Lasso, what it does is that it actually helps you identify which feature is the most contributing feature. Which features are the most important features for predicting your values. Say, for example, Lasso say, okay, let's just remove W naught for the time being. Lasso says that, say, W1 is your blue feature. So what it does is that it says that W1 is the highest value, and all these things that you see here, they can simply be made zero, because around 80% of your prediction can be made correct just by predicting, just by getting W1 right. It says this feature X1, your time spent in doing self study matters the most to get the maximum grade, is sufficient to predict your grade. So when only this feature is greater than 0, that means that x1 is the most important feature. Everything else is not so important. And then the second best important was this red line. So let's just say that W2 is the second best important feature. So that is x2 is the second best important feature, because W2 was greater than 0. This red line was greater than 0 for quite a bit time. So W2 and W1 together can give you around 85% of your correct answer. When you say that, okay, the third and fourth and fifth best features were also important, say around when was lambda is equal to 10 to the power, say minus 1. So you set W3, sorry, W3, W4, W5. Okay, W5. When you have all these W1, W till W5, all were greater than 0. So all X1 to X5 features were important, and now you are able to make 100% correct prediction. And all the other things were useless, so you have put all the other features to 0. Because only 5 features were important, right? As we said before, only 5 features are informative, for other 5s are useless. So you were able to figure out which 5 features are important based on if those W's are greater than 0 or not. If those W's are equal to 0, that means they are not even important. So as you increase lambda, you are making your model more simple, and you are asking the model that only find me those important features in Lasso, only find me those important features which contributes the most in making my prediction. So when you say that only blue and red are important, that means that they are removing almost all the important features to make sure that you have are at least 70 to 80% correct. When you added W3, you made sure that, okay, fine, W3 is also important, but not so important. W3 is also important. So you added some amount of increased your prediction power. And when you said W4 is important, you increase your more predictive power. When you added W5, you may increase your more predictive power. But in Ridge, what it does is that it slowly goes to 0. It does not go 0 like suddenly. As you see in Lasso, it suddenly drops to 0. Here, it slowly goes to 0. It will slowly make all these numbers to decay to 0. So even though it is able to say the W2 is the blue curve is very important, but it slowly, it also keeps on dragging that, oh, I will not put them to 0 because they are all important. I cannot choose which one is more important, which one is not. So they keep on dragging. Even till 10 to the power 5, at 10 to the power 4, when you made your lambda 10 to the power 4, it's still trying to make sure that no, all these features are very important. I can't send anyone to 0. Here, lasso is simply says that these features are not important. I will just remove the cut off very easily. So that's the difference between Ridge and Lasso. Both are important. Lasso is able to identify which features are the most contributing feature. If you ever in your problem face that, tell me, if you are given a model, say if you are given Y and you are given 10 features or maybe 100 features, and you want to know which among these 100 features are the most important features, apply Lasso. It will quickly find out which or among these 100 features, which are the top few features that you really need to predict your answer. All those out of 100, you will drop about 70-80% of your features will be dropped, because you were able to identify only these features are important to make prediction. And once you know that these are the important features, then apply any ridge regression or lasso if you want to apply, and then make your prediction. In general, in real world, you will get not 10 features, you will have like hundreds of features which you need to find out, is this feature even important for predicting? And for that, you apply lasso. It will quickly able to identify you which features are important. You see, it simply sets them to 0, but ridge will keep on dragging even the sometimes unnecessary information. Say for example, it seems to be close to 0, but there are some points that are not close to 0. There are some points some still above. It will keep on dragging. So you will not be able to identify which one is the important feature. Here you will simply identify because they will put everything to 0. Okay, so coming back to this table, ridge. In ridge regression, the coefficients of the correlated predictors will be similar. So they will make all the W1s very close to each other. In lasso, some predictor will be very large and rest will be zeroed. They will simply put everything to close to 0. As you see, when you increase your ridge, they became very close to each other. And in lasso, they will simply put to 0. There will be very high and there will be some very close to 0. That's what lasso does. Now, this is most important. Ridge works well if there are many large parameters of the same value. So if you have many parameters, many W1 to W10s, which are sufficiently very large, you will try to bring them small. But what lasso does is that it will generally tend to do well if there are small number of significant parameters and others are close to 0. So what it does is that it simply puts all the unnecessary parameters to 0 and only keep those parameters that are necessary. That's it. This was the entire table, and I will now stop because I have ended up taking 18 more minutes today. Okay. So did I answer the person's question who asked me?
Yes, sir, very well. It's quite clear with the proper examples and the curves. Thank you so much,
Okay,
sir.
okay. Thank you again. I'm happy if you are able to follow. I ended up taking too much time today. I'm very sorry. I will share the tutorials and everything now. I think I took
Okay, sir.
so much time today. Okay. Give me 1 second. Let me just share these. Uh, okay. Okay. Uh, okay. Can you please compare, check uh, if you can see the notebook? Okay. Thank you again. Uh, you are able, if you are, so we can close the lecture now. Uh, Make sure that you go through this notebook. I have shared all the notebooks details. If you're not, if you by any reason, if you're not able to, if you have not seen the other lectures, let me just share. There's something else too. Okay. So this is the drive link that contains all the things, all the materials that I have covered, and plan to keep adding all the materials that I will be teaching in this drive link. I will see if the other person, Roshan, he is going to take the next class. So I will see if he can also add to the same drive link. But this is the drive link that I have kept all the materials that I was sharing with you. Okay, next class, Roshan will be teaching. Uh, and hope you uh, you will ask questions similarly to him too. Okay, thank you again. So we can close the lecture today. And sorry for keeping you here for so long. We can end the lecture now.
Sure, and on behalf of all the participants, I would like to thank you for your sharing of knowledge. Thank you so much.